So here I've got some tabulated and lattice energies. And notice in the previous slide, we were looking at the energy that was released when you had anions and cations in the gaseous form coming together to make the lattice solid. Usually you report lattice energies and the energy required to take it apart, to separate all the ions out to, infinite distance. So these are all positive numbers, but these would correspond to, the reverse of this is how much the ions like to be together. So we can look at these in kilojoules per mole. You notice they're all fairly high numbers. There's actually a lot of potential energy in bringing ions close to each other. But we can see some interesting trends here. So for example, if we take a look at lithium, we can see that as we look at the partners of lithium in the salts going down the periodic table, we can see that the energies get lower and lower. And that's a trend that follows pretty much across the board. There's, here it gets smaller and smaller. Here it doesn't, aluminum is a little different than there. Aluminum is relatively non-metallic for a metal. It's less metallic than most metals, so it doesn't quite behave exactly the way the rest of them are. But most of these, we have things that are very metal reacting to things that are very non-metal. We see a pretty substantial trend of always going down here. But then if we look at the interaction with oxygen, we can see that it's much larger. The interaction with lithium, of course, remember it would be Li2O, is that lithium oxygen interaction is much bigger. So there's sort of two different trends here that we can see that are really fairly easily explained when if we just look at the shape of Coulomb's law. So Coulomb's law said the electrostatic energy will be charge 1 times charge 2 divided by the distance between them. So if you have bigger charges, you have more favorable energy. If you have something like calcium oxide, that's a +2 on the calcium and a -2 on the oxygen. That's essentially 4 times as much energy as if calcium just had a plus and oxygen just had a single minus. So bigger charges, if you double, triple the charges or whatever, you're gonna have more favorable energy. The other thing is if you have larger ions, like going from lithium fluoride to lithium chloride, that chlorine is bigger and therefore it can't get quite as close. Therefore this R is bigger and therefore the energy is smaller. Larger ions, they can only go a certain distance apart, so there's less favorable energy associated with that. So those are the two effects you see. As the ions get bigger, the lattice energy is not quite as big, but if the charges are big, you get a lot of energy. And if both things are happening, if you're increasing the charge and increasing the size effect is relatively small. It's very consistent, but it's quite small. As the radii get 10% bigger, the energy gets 10% lower. Whereas, charges, if you go from +1 to +2, that's not a change of 10%. That's a change that's double.